Thermofluid systems are complex systems that combine the principles of thermodynamics and fluid mechanics. These systems are essential in powering a wide range of industries and technologies, from energy generation to heating and cooling. The slide provides a detailed illustration of a thermofluid system, showing the various components like pipes, valves, and heat exchangers. I'll use this visual to give an overview of how these systems work and their importance in our modern world. Thermofluid systems are critical for efficiently converting, transferring, and managing energy in various applications. Understanding the intricacies of these systems is key to advancing technologies and improving energy efficiency across sectors. Thermofluid systems are complex engineered systems that rely on the fundamental principles of thermodynamics, fluid mechanics, and heat transfer. Understanding the laws of thermodynamics and how thermodynamic properties behave is crucial for analyzing and designing these systems. Fluid mechanics concepts like fluid flow, pressure, viscosity, and other properties must also be well understood. Heat transfer through conduction, convection, and radiation plays a key role in thermofluid systems and needs to be carefully analyzed and optimized. This slide provides a high-level overview of the key technical foundations that underpin thermofluid systems. I'll dive deeper into each of these areas in the upcoming slides to give you a comprehensive understanding of how these systems work. Thermodynamics is the study of energy transformations, focusing on the relationship between heat, work, and temperature. It provides the fundamental principles governing the transfer and conversion of energy in various systems. The first law of thermodynamics states that energy can be transformed from one form to another, but it cannot be created or destroyed. This establishes the principle of conservation of energy within a thermodynamic system. The second law of thermodynamics states that the entropy of an isolated system not in equilibrium will tend to increase over time, approaching a maximum value at equilibrium. This law describes the natural tendency of energy to become more disordered. The three fundamental laws of thermodynamics that govern the behavior of energy and entropy in the universe. The first law states that energy can be transformed but not created or destroyed. It establishes the principle of conservation of energy. The second law says that the entropy, or disorder, of an isolated system will tend to increase over time as it approaches equilibrium. This law governs the direction of natural processes. The third law states that as a system approaches absolute zero, its entropy approaches a constant, usually zero, value. This establishes the unattainability of absolute zero and provides a reference point for measuring entropy. These three laws are foundational principles that underpin our scientific understanding of energy, matter, and the natural world. Thermodynamic properties are essential for understanding and modeling the behavior of thermofluid systems. Temperature, pressure, density, internal energy, and enthalpy are key properties that describe the state and performance of a system. Temperature measures the average kinetic energy of molecules, indicating how hot or cold a substance is. Pressure is the force exerted per unit area, influenced by the motion and collisions of molecules. Density is the mass per unit volume, which affects the behavior of fluids and component performance. Internal energy is the total energy contained within a system, including kinetic and potential energies of the molecules. Enthalpy is the sum of a system's internal energy and the work done, representing the total available energy. Thermodynamic processes describe how a system changes from one state to another. There are three main types of processes: reversible, ideal, no energy loss; quasi-static, infinitely slow, near equilibrium; irreversible, real-world, energy dissipation. Understanding these fundamental process types is crucial for analyzing the efficiency and performance of thermofluid systems. Reversible processes are the ideal, with no energy loss, while irreversible processes involve real-world energy dissipation. Quasi-static processes occur infinitely slowly, maintaining near equilibrium conditions. These process types have important implications for the design and operation of thermal and fluid systems. Fluid mechanics is the study of how fluids, including liquids and gases, behave and move. Understanding fluid mechanics is crucial for designing and optimizing a wide range of engineering systems, from hydraulic machinery to HVAC systems. Key concepts include fluid statics, fluid kinematics, and fluid dynamics, which describe how fluids behave under various forces, how they move, and how they interact with their surroundings. Mastering these fundamentals is essential for designing efficient and effective thermofluid systems. The image on the right provides a visual representation of some of these fluid mechanics principles, showing flow, pressure, and other properties. Bernoulli's principle is a fundamental concept in fluid mechanics that describes the inverse relationship between pressure and velocity in a fluid flow. As the speed of a fluid increases, the pressure within the fluid decreases. This is a crucial phenomenon for the functioning of airplane wings and other aerodynamic structures. The faster-moving air above the wing creates lower pressure, generating an upward lift force that allows the aircraft to fly. Bernoulli's principle has numerous practical applications in engineering, such as the design of carburetors, the operation of ventilation systems, and the analysis of flow through pipelines and nozzles. Understanding this principle is essential for the optimization of fluid-based systems and the design of efficient, high-performance engineering solutions. Viscosity is a crucial property that measures a fluid's resistance to flow. It's key for analyzing pressure drops and heat transfer in thermofluid systems. The friction factor is a dimensionless coefficient that quantifies the energy losses due to wall friction and pipe flow. This can have a significant impact on system performance. Pressure drop, the decrease in pressure along a pipe, is heavily influenced by both viscosity and the friction factor. Understanding these properties is essential for designing efficient thermofluid systems. This slide provides a high-level overview of these important concepts. I'll dive into more detail on each one and explain how they relate to overall system design and performance. Pipe flow can exist in two distinct regimes: laminar, where fluid particles move in parallel layers, and turbulent, where there is chaotic mixing of fluid particles. The transition between these regimes is characterized by the Reynolds number, a dimensionless parameter that captures the ratio of inertial to viscous forces. As fluid flows through a pipe, it experiences two types of pressure losses: major losses due to wall friction and minor losses due to changes in pipe geometry, such as bends, expansions, or contractions. These losses can be quantified using empirical equations and friction factor correlations. The Darcy-Weisbach equation is a fundamental equation used to calculate the major pressure losses in pipe flow. It relates the pressure drop to the pipe length, diameter, fluid velocity, and a dimensionless friction factor that depends on the pipe roughness and flow regime. Pumps and compressors are critical components in thermofluid systems, responsible for moving and pressurizing fluids and gases. Centrifugal pumps use an impeller to create pressure and flow, while positive displacement pumps like piston and gear pumps apply mechanical force to displace the fluid. Compressors increase the pressure of gases by reducing their volume. Common compressor types include reciprocating, screw, and centrifugal, each with their own advantages in terms of efficiency, capacity, and application. This slide provides an overview of the key differences between pumps and compressors and the main technologies used in each category. Centrifugal pumps are a common type of industrial and municipal pump. They use an impeller to convert rotational energy into pressure and flow. This makes them highly efficient and able to handle large volumes of fluid. Positive displacement pumps, like reciprocating and rotary pumps, work by trapping a fixed volume of fluid and forcing it through the discharge pipe. These are well suited for high-pressure applications and handling viscous fluids. Axial compressors use a series of rotating blades to increase the pressure of a gas, like air. They are commonly used in gas turbine engines and are known for their high flow rates and efficiency. Centrifugal compressors use an impeller to increase the pressure of a gas. They are often used in industrial applications, like compressed air production, and have a compact design with high pressure ratios. Pump and compressor performance is crucial in thermofluid systems. Key metrics include flow rate, pressure rise, power consumption, and efficiency. The chart shows how these metrics vary with flow rate. Higher flow rates lead to increased pressure rise, power consumption, and efficiency. Understanding these relationships is essential for selecting equipment and optimizing system design. Carefully considering these factors is key when designing and optimizing thermofluid systems. Heat transfer is the fundamental process by which thermal energy moves from a hotter region to a cooler region. There are three main mechanisms of heat transfer: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact between molecules, commonly seen in solid materials like metal rods. Convection is the transfer of heat through the movement of fluid, creating circulation patterns as warmer fluid rises and cooler fluid sinks. Radiation is the transfer of heat through electromagnetic waves, allowing thermal energy to travel through vacuum, as seen in solar radiation reaching Earth. Understanding these heat transfer principles is crucial for designing efficient thermofluid systems, from HVAC equipment to power generation plants. By applying the right heat transfer techniques, engineers can optimize energy efficiency and improve system performance. Heat is transferred in three main ways: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact between molecules from hotter to cooler areas. This is the primary mode of heat transfer in solids. Convection is the transfer of heat by the movement of a fluid, like air or water. It can be natural or forced, and the rate depends on fluid properties and flow. Radiation is the emission of electromagnetic waves by a heated surface. Unlike conduction and convection, radiation can transfer heat even in a vacuum. The rate is proportional to the fourth power of the absolute temperature. Understanding these three heat transfer mechanisms is crucial for many engineering and scientific applications. Heat exchangers are devices used to transfer thermal energy between different fluids, solids, or between a fluid and a solid. There are several main types of heat exchangers, including shell-and-tube, plate, fin-and-tube, and compact designs. The fundamental principles of heat transfer in heat exchangers involve conduction, convection, and radiation. Key design considerations for heat exchangers include efficiency, pressure drop, material compatibility, and cost. Effective heat exchanger design is crucial for many industrial processes and HVAC systems to ensure efficient heat transfer. Shell-and-tube heat exchangers are the most common type, with a series of tubes inside a shell. Fluid flows through the tubes while another fluid flows around the tubes, enabling efficient heat transfer between the two. Plate and frame heat exchangers use a series of thin, corrugated metal plates stacked together. This design offers a high surface area for heat transfer in a compact footprint, often used for high-pressure or temperature applications. Compact heat exchangers are designed for high heat transfer rates in a small size, using techniques like fin tubes or microchannels. They are commonly found in automotive, HVAC, and aerospace applications where space is limited. Heat exchangers are crucial in thermofluid systems, enabling the transfer of thermal energy between fluids. This allows for important applications like heating, cooling, and energy recovery. Careful analysis of factors like fluid flow, heat transfer coefficients, and geometry is essential to optimize performance and minimize losses. Key design considerations include material selection, configuration, e.g. parallel, counterflow, and heat transfer enhancement techniques. Analytical and computational methods are used to evaluate performance and guide the design process. Boiling and condensation are fundamental phase changes that occur in thermodynamic systems. As a liquid is heated, it reaches its boiling point and transitions into a gas. Conversely, as a gas is cooled, it reaches its condensation point and transitions back into a liquid. During these phase changes, there is a significant exchange of latent heat, the energy absorbed or released when a substance changes state without changing temperature. Understanding the factors that affect boiling and condensation points, like pressure, composition, and surface interactions, is crucial for designing efficient heating, cooling, and energy conversion systems. Phase changes are transformations between physical states like solid, liquid, and gas. These changes are driven by temperature and pressure. Phase diagrams visualize the stable phases of a substance under different conditions. They help predict the phase of a material and the conditions for phase transitions. Understanding phase changes is crucial in fields like thermodynamics, materials science, and cryogenics. The phase diagram on this slide shows the solid, liquid, and gas phases of water under different temperature and pressure conditions. The psychrometric chart is a powerful tool used by HVAC engineers to analyze the properties of moist air, including temperature, humidity, dew point, and more. It allows us to understand the behavior of air in heating, ventilation, and air conditioning (HVAC) systems, which is crucial for ensuring efficient and comfortable indoor environments. Humid air exhibits unique characteristics that must be accounted for in HVAC system design. Understanding the principles of psychrometrics, such as the relationship between temperature and humidity, is essential. Applying psychrometric principles allows HVAC professionals to optimize system performance, ensuring the right balance of temperature, humidity, and air quality. This helps improve energy efficiency, occupant comfort, and overall system reliability. Psychrometric processes are the changes in temperature, humidity, and other air properties as it undergoes transformations. The key processes are heating, cooling, humidification, and dehumidification. These are essential for maintaining comfortable and efficient indoor environments in HVAC systems. Understanding these processes is crucial for designing and optimizing thermofluid systems that handle air and moisture effectively. Let's dive into each of the 4 key psychrometric processes in more detail. HVAC systems are essential for maintaining comfortable and healthy indoor environments. They regulate temperature, humidity, and air quality to ensure occupant comfort and energy efficiency. HVAC technologies include furnaces, air conditioners, heat pumps, ductwork, thermostats, and air handling units. Advancements in HVAC design, materials, and controls have led to improved energy efficiency and enhanced indoor air quality. HVAC systems are used in residential, commercial, and industrial settings to meet the diverse needs of modern buildings. Air conditioning and refrigeration systems work by removing heat from a space or substance and transferring it elsewhere. This is achieved through the refrigeration cycle, which uses a refrigerant gas that undergoes phase changes to absorb and release heat. Compressors, condensers, and evaporators work together to efficiently move heat and provide cooling. Air conditioning is commonly used to cool homes, offices, and other indoor spaces, providing comfort and temperature control. Refrigeration systems are essential for preserving and storing perishable goods, such as food, medicine, and scientific samples. Industrial processes, data centers, and transportation also rely on specialized cooling solutions. Global thermal energy storage capacity has reached 30 million megawatt-hours as of 2021 and is expected to grow significantly in the coming decades. The thermal energy storage industry is projected to reach a market value of $100 billion by 2027, driven by the increasing adoption of renewable energy sources. There are currently over 10,000 existing thermal energy storage installations worldwide, with many more in development. Thermal energy storage plays a crucial role in decarbonizing energy systems by enabling the efficient use of renewable energy sources. TS technologies store heat or cold energy for later use, helping to balance supply and demand, reduce peak loads, and integrate intermittent renewables like solar and wind power. Commonly used TS methods include sensible heat storage, latent heat storage, and thermochemical storage, which can store energy from various sources, including solar, waste heat, and off-peak electricity, for use when needed most. Renewable energy sources like solar, wind, and hydroelectric power are crucial for reducing our reliance on fossil fuels and addressing climate change. These clean energy alternatives offer sustainable solutions for power generation. However, integrating renewable energy into existing power grids presents technical challenges. Grid stability, intermittency, and storage requirements are some of the key issues that need to be addressed. Combining renewable energy with conventional power sources like natural gas or biomass can create hybrid energy systems. Hybrid systems leverage the strengths of both technologies to improve reliability, efficiency, and overall sustainability of the energy mix. The transition to clean, renewable energy sources like solar, wind, and geothermal can significantly reduce the carbon footprint and environmental impact of thermofluid systems. Designing thermofluid systems with a circular economy in mind, focusing on reuse, recycling, and sustainable materials can minimize waste and promote long-term sustainability. Improving the energy efficiency of thermofluid systems through advanced techniques and technologies can significantly reduce energy consumption and associated environmental impacts. These 3 key areas, renewable energy, circular economy, and energy efficiency, are crucial for improving the environmental sustainability of thermofluid systems. Computational fluid dynamics, or CFD, enables the simulation of fluid flow and heat transfer around complex geometries. This provides valuable insights into the performance and behavior of systems before physical prototyping. CFD software offers advanced numerical algorithms and visualization tools that allow engineers to thoroughly analyze and optimize the performance of thermofluid systems. CFD modeling is essential for the design and optimization of heat exchangers, HVAC systems, and other thermal management applications. This ensures efficient heat transfer and fluid flow in these critical systems. CFD modeling is a powerful tool for creating detailed digital representations of fluid flow systems. It involves incorporating factors like geometry, material properties, and boundary conditions to build accurate models. Careful model construction is crucial for ensuring the simulations are reliable and representative of real-world conditions. The model is divided into a grid of small computational cells, a process called meshing. This discretization allows the governing equations to be solved numerically, providing a comprehensive understanding of the flow field. Advanced computational algorithms are used to solve the complex partial differential equations that describe fluid flow and heat transfer. CFD software iteratively calculates flow properties like velocity, pressure, and temperature throughout the model domain. The result is a detailed visualization and analysis of the fluid flow, which can provide valuable insights for engineering and design. Thermofluid systems are critical components in many industries, from manufacturing to buildings to transportation. Optimizing these systems can lead to significant improvements in efficiency, energy consumption, and environmental impact. We'll explore 4 key areas for thermofluid system optimization: process simulation, digital twins, intelligent controls, and sustainable design. Process simulation using advanced computational fluid dynamics, CFD, models allows us to identify opportunities for improved efficiency and performance. Digital twins, virtual representations of physical systems, enable us to test and validate design changes before implementation and support predictive maintenance. Implementing smart control systems that dynamically adjust parameters based on changing conditions ensures thermofluid systems operate at peak efficiency, reducing energy costs. Incorporating sustainable design principles, like waste heat recovery and renewable energy integration, can minimize the carbon footprint of these critical systems. The field of thermofluid systems is rapidly evolving, driven by advancements in technology, the pursuit of greater efficiency, and the need for sustainable solutions. As the world transitions towards renewable energy sources, thermofluid systems will play a crucial role in integrating these technologies. Innovations in heat pump design, thermal energy storage, and smart controls will enable seamless integration of renewable energy. The incorporation of AI and automation will revolutionize the way thermofluid systems are designed, operated, and optimized. Advanced algorithms, machine learning, and predictive analytics will enhance system performance, improve energy efficiency, and facilitate predictive maintenance.